Hey there, welcome back to this channel. In today's video, we are going to be talking about electric charges under the topic electricity. Initially, I released a video on direct current where we talked about the electrochemistry of batteries, which is the major source of direct current, the major source of power for direct current. So how a battery works, I have made a video of that. I'm going to link it down in the description below so that you can watch it and understand. But of course, this is the starting point of electricity, the electric charges. I'm seeing to make a video on the history of electricity, but you don't need that for your Jamb. So that could come later. So I'm starting with where the scope of the study starts from, which is electric charges under electricity. Now, what are electric charges? The first thing you should have in mind is that it is the fundamental nature of all atoms. So I said it's fundamental to all atoms. Electrical charges are fundamental properties of atoms. So if they are fundamental properties of atoms, it basically means that, and we know already that all atoms, atoms make up matter. So it means all matter are composed of atoms. So therefore, it means that it is a fundamental nature of all matter. So it means that everything you see around you have an electrical property because they are made of atoms, and atoms, of course, have electrical charges as one of their fundamental properties. Now, how do we know about that? Because from the discoveries of several scientists, J.J. Thomson, and Rutherford, and all of them, Niels Bohr, and all of them, we have known that the atom is made up of the electron, the proton, and the neutron. Now, these are the three charges, these are the three particles that an atom is said to be composed of. And according to Niels Bohr, we know that we have an atom comprises of a nucleus or a core or a center, which is composed of those protons and neutrons. Then surrounding them and moving at the near speed of light are electrons. So electrons are moving around them at very great speed. So we do know from here also that these two guys, protons and neutrons, are static, they are stationary, they're not moving, only electrons move. So you also need to understand, even in this context of static electricity, that only electrons move, only electrons get transferred from one object to the other. Only electrons do what? Get transferred from one object to the other. Now, what are electrons? Now, of an atom, of all atoms, an electron is the negatively charged particle of that atom. Negatively charged particles. Or you see in some textbooks, it just says electrons are negative charges. And protons are the positive charge, the positively charged particles, the positively charged particles of the atom. While neutrons are the ones that are neutral. Neutrons are the ones that are neutral. And you will know from basic chemistry, we've said it before, so that all atoms have equal number of protons and neutrons. So for example, for an element magnesium, it's going to have 12 electrons as well as 12 protons. So what that means is that all atoms in their ground state, or basically atoms found in their ground state are what? Electrically neutral. So atoms in their ground state are what? Electrically neutral. Now, how do they gain charges or lose charges? Now, when we say they gain charge or lose charge, it means that they will exit this ground state and they will become excited. They become what? Excited. So in that state where they either gain electricity or lose, we say they are become excited. Now, when you say something is positively charged, if I say something is positively charged, we have said that protons don't move, only electrons move. So, and protons are positive charges, so you might begin to think that it is the protons that are moving to that thing, that is why the thing is positively charged. But no, if you say something is positively charged, it only means that that thing has more protons than electrons in it. And how does that happen? It happens when a, a an atom loses electrons. When an atom loses electron or gives an electron or donates electron to another atom, it means that the proton number will have reduced. So, for example, magnesium is capable of donating two of its outermost electrons. So, if it donates that, it means that it will have two more protons than the number of electrons that it now has. So, it will be Mg2 plus. So, we'll say that it is positively charged here. Actually, it is not that it has gained a positive charge, only that it has more positive charge in it than the number of electrons that it has. So here, so if I wrote Mg here, this is just magnesium atom, but this guy has 12 electrons, while this guy has 10 electrons. So if this guy has 10 electrons and what? 10 and 12 protons. So it means that it has what? Plus 2 charge. Do you understand? So that's why we come up with this 2 plus charge. But we're not getting into chemistry now, where I'm just trying to emphasize on what we mean by positively charged body. So if I say a body is positively charged, it means it has lost electrons and has more protons than electrons at that time. And if I say it is negatively charged, it means that, when it gives out to someone, it means that guy is going to have more electrons now than it initially had. So the guy that receives more electrons is going to be what? Negatively charged. Do you understand? Negative charge. That is, the proton will be less than the electrons for a negatively charged body. Now, and when I say it is electrically neutral, as we have said, it means that our protons equate electrons. All right. Now, what is the unit of charges? The unit of charges is Coulomb. The unit of charge is Coulomb, electrical charges. And it is named after Charles Auguste Coulomb. Charles Auguste Coulomb. All right. Now, you see, this Coulomb is a very great quantity, in terms of quantization. So charges are quantized, and they are quantized in the unit of Coulomb. But Coulomb is a very great quantity. So, for example, an electron has a charge of, if you remember from basic chemistry, we know that one electron is equal to 1.67 blah 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 times 10 to the minus 19 Coulomb. So you see how much one electron is. So it means that if you have 1 Coulomb from electrons, you need about 6.25 by 10 to the 18 electrons to make 1 Coulomb of electricity. So that's why Coulomb, we said, is a very great value, is a very great quantity. Now, one of the things that was discovered was that according to the history now, so first it was more like publicly showcased by Thales of Miletus. Thales of Miletus in ancient Asia. So Thales was the first scientist in fact to publicly show that static electricity or electricity as a property actually existed. And it came out, and this was because it was discovered that amber, when rubbed with with the skin of an animal, which was their garments then, so when rubbed with the skin of an animal, would gain negative charge. So when you rub amber with the amber became negatively charged, and it could attract small pieces of substances, very tiny pieces of materials to itself. And then it seemed magical because it was the first time I was seeing something like that. So, and you see that amber is actually the root word for electricity, because amber in ancient Greek is called electron, and this is the word from which electricity is gotten from. And of course, the word electron. So, electricity is the word for amber in ancient Greek. Okay, so discover that when you rub this and this guy became what? Negatively charged, and then the 4 became positively charged. So, from further experiments in the 18th century, it was also discovered that when you rub not just 18th century, very, very much earlier than then. When you rub glass rod, for example, glass rod with silk. So the glass rod usually gained the positive charge. Now, it wasn't really explained why the glass rod gained the positive, while the silk gained negative charge. Then, when you rub ebonite rod with 4, the 4 always gets what? The positive charge. Just get that. Now, the reason I'm emphasizing this is because I've seen a Jamb question where a question like this is asked about, in fact, about ebonite rod. So the ebonite rod will therefore get what? The negative charge. When you see the 4, 4 always gets the hair. So even the hair on your body, your hair, if you comb it, when you rub comb on your hair will get the what? Always gets the positive charge. And then the comb gets what? The negative charge. That's why if you rub a piece of plastic too, or rubber on your hair, you can use it to attract tiny little piece of paper. I would have demonstrated for you now. Just, especially when your hair is very dry, rub plastic on your hair, maybe your biro or something like this, rub it vigorously on your hair and tear a tiny piece of paper like this. Let me get a tiny piece of paper. See something as small or tiny as this. You see that you'll be able to pick it up with that plastic. Now, with that thing you rub on your hair, why? Because the guy is going to get a negative charge. So, and we see that this guy, since that guy will now be able to attract other things. This was why the first law of electrostatics was proposed. Now, the one thing you should also know, of course, is that, it could be in your mind that how did we name these positive and negative charges? One thing you should know is that positive and negative charges, these words, are basically properties. They are not values per se. How do I put this? So, for example, in mathematics, if you hear +1 and -1, it could mean how much someone has more than something has more than something, or how much something has less than something when you hear plus or minus. But here, it is just a property. So we could have assigned, or it could have been assigned white and red, or white and black. You understand? So just like white and black is for a color that appears white, and something that appears white and something that appears black. I've said black and white are not colors. So for something that appears white, something that appears black, just the way we assign those names to them is the way we have assigned positive to the one that doesn't really attract things to itself again. Why we address negative we ascribe negative rather to the one that attracts other things to itself. And that word was actually coined by the American scientist Benjamin Franklin. Benjamin Franklin was the one who came up with the name positive and negative charges. Is that okay? So, and I've told you it's just the nature of those charges that we use to describe them. Now, and so because we noticed that some things now attract each other, others repel each other, then it was the law of electrostatics was proposed. The law of electrostatics. And what does this say? What does this state? Now, the law of electrostatics says that when the charges are alike, we call them like charges, they will repel. And when the charges are unlike, they will attract. So law 1 is saying that when positive meets positive, there is a repulsion. But when positive and when negative, of course, meets negative, there was a repulsion, a pushback, a push away. But when positive and negative meet each other, more like when boys and girls meet. All right. So like charges and like charges, that is. Okay, so that's the law of electrostatics. Now, how do we explain the concept of this push and pull that happen to these charges? Now, the concept of electric field now needs to be understood. The concept of electric field. So, in order to understand how these things happen, because it was also noticed that it is distance based. That force of attraction and repulsion is distance related. So it means that there is a particular circumference, and there is a particular area over which or around which that influence of electricity is felt, or we call it the electric force, where that electric force is felt. So we call it what? The electric field. So for a point charge, a point positive charge, for example, is going to have an electric field surrounding it. So if I put my point positive charge here, so for a positive charge, since we said that it wasn't discovered to be the one attracting substances to itself, then it means that it's probably repelling substances away from it. So we represent its field lines. We represent first electric field, that region around which the electric force is felt, represent that region as field lines, with lines to explain, to show that region over which that electric force is felt. So that's how we define the electric field. The region around which an electric force is felt, or the region around which a test positive charge, a test charge placed, a test charge, the region around which a test charge, we experience a force on it. So that is an electric field of another charge. Do you understand? So, but by the way, just get the fact that they are represented in field lines. So the field lines are always going all out. Why? Because it looks to us like, or the scientists did, that it was always repelling substances away from itself, while the negative charge, when you draw the field lines from a negative charge, is going to come all in. So that is why we said that if you rub that plastic on your hair or your comb on your hair and you use it to pick a piece of paper, you see it's going to be attracted to that piece of paper. So that is why we see that, okay, maybe the charges, the field is such that it is attractive towards it. Do you understand? So we represent it in field lines that are with arrows going into the charge, while the arrows are going outside or out of the charge. Now that is that for electric field. So what if we now brought both of them close to each other? So it means that if a positive charge, positive point charge, was, I'm circling it just to, to separate it. I mean, I just want to make it concentrated, kind of. All right, and I have a negative charge here. So what you're going to notice is that all the charges on its field lines are going to go in this direction, in this direction, in this direction. So we draw them this way. All right. So what you will notice here, first, let's see, is going to always go outside from positive. And since it's going inside at negative, so it will look like it's going from positive to negative. So that's the way you should understand it. You should always go inside. When you are drawing negative, that your line must go inside, the arrows must point inside. But when you draw it on the positive, it must point away from that positive. It must point away from that positive, away from the positive. All right. So if it's pointing away from positive and always pointing towards the negative, definitely when you bring them close enough, the reason why a positive charge will not attract a negative charge is because of what? The field lines always go from positive to what? To negative. So then we see what? An attraction here. An attraction. But how do we notice the repulsion? I'm going to be using just a positive and a positive. I'm not going to use negative and negative another because of time. So what you see is that it's going to go all out here, go out here, go out here, go out here, go out. Here also out. So what will happen is that they will never touch each other because it's always going out. So in other words, you are going to see a repulsion, a push away. Do you understand? So this point where there is nothing acting here is called what? It's called the neutral point. It's going to be called the neutral point. Now we're also going to talk about this thing in magnetism, and you're going to see how electric field lines are somehow similar to B field lines, but with essential differences. So one thing you will see here is that they are not continuous. The electric field lines are not continuous. Why? Because they always start from positive and end at negative. They are not starting from positive and going to negative and coming back. But with magnetic fields, you are going to see that that's the way it is. So that's that. And then we can have a separate charge by itself. We can have a charge on its own, exists in the atmosphere. All right. So we can have a charge on the Earth. So we're still going to get to Earthing. So what do you see here? And a repulsion will happen here. A repulsion is going to be noticed here. All right now. So we now understand what these guys have, how these guys happen to do this. Now, basically, most of the substances that we have discussed here, glass rod, comb, plastic, all those things, they are all insulators. They are substances, even though they have electrical property, as I've said, they are called insulator. And why are they called insulator? So that is the division. There are two divisions in which, two basic divisions in which substances in the universe are divided based on their effect on electricity. The ones that are not really affected by electricity, such that they do not allow electricity to pass through them, they are called insulators. While the ones that allow electricity to pass through them, they are called what? Conductors. Conductors. Another name for insulator is dielectric. Dielectric. All right. Now there is another category that is in between these. We call them semiconductors, but we will not be discussing them now, maybe until we get to photo emissions and all. So, but I'm going to talk about it when I'm discussing the history of electricity. You will know what semiconductors are. I mean, and of course, they become more conductive with the increase in temperature, but ordinarily they are just midway between, they conduct a little, not as much as conductors will do. Now, conductors are metals, any metal, you just name it, tin, lead, steel, also metal. And of course, a common question you see in Jamb is this allotrope of carbon. So diamond, we have allotropes of carbon are diamond, graphite, and soot. So diamond and soot do not conduct electricity, but graphite does. Graphite does. And you already know. So that's why pencils can conduct electricity. If you've ever used a pencil, I mean, someone has done it before, not me. So the person tried to plug in something into the electric circuit, and he used a pencil that the razor, the hair that removed. So he got shocked a little because that black stuff inside the pencil is called lead. So it's composed of lead and graphite. So, and graphite can conduct electricity as much as lead can also conduct electricity. So those are all conductors. So we said metals, basically all metals. We mentioned graphite as a very good example. Then this one, plastics, rubbers, glass, ceramics, they are non-conductors. All right. Now, okay, yeah, just call them non-conductors or insulators. All right. So that is one thing with them. So, but they do have electrical property, insulators, and that's why they can be charged. So these things that are being done here, glass rod plus silk is a method of charging. In fact, let's get to that already. So how do we charge them? Methods of charging. Now there are three methods of charging substances. There are three major methods. One is by friction. The other is by contact, and the last is by induction. So we'll call it hydrostatic induction. Okay, so with the friction is the way by which you charge non-conductors or insulators. So what you see here is that everything we always do is just to rub, and that's friction, right? So glass rod, you rub silk, ebonite rod, you rub comb, comb, you rub on your hair, plastic and all that, you rub on your hair. So that is what friction. So what happens is this. So let's say this was a piece of material that you're rubbing, and this is the cloth that you're rubbing. Now, both of them, the reason why they are not conductors is because they have equal charges, equal amount of positive and negative charges. They all balance out, and the electrons are not localized. Now I'm going to talk more about it later on why these guys are also non-conductors. Electrons are more localized into the core of the atom than it is in metals. In metals, the electrons are more available on the outside of the material. So with this, electrons are held closely together in the atom. So we have the charges balance each other out. So what you do when, so this is my guy now, this is my guy, my piece of cloth on, so let's say this is my silk on my glass rod. Now I begin to rub and rub and rub and rub and rub. So by the time I rub, what I'm doing is I'm dislodging these positive and negative charges. So as I dislodge the positive and negative charges, so what will happen is that some electrons will move from one to the other. So say if this was glass and silk, so this is my glass and this is my silk. Remember, the glass is going to gain the positive charge. So what does that mean? It means that electrons are going to move away from here and be added to this. So what happens at the end of the day is that this silk is going to get more positive charge. It's going to get negative charge rather, more electrons rather. Electrons are going to move here. So this guy is going to get more electrons. And electrons are going to leave here. So this guy is going to have more positive charges than negative charge. So we say the glass rod is what? Positively charged. All right. So keeping in mind that it is only electrons that move. So electrons are being exchanged. But also one thing that was also found out is that the law of conservation of charges is observed here. The total number of charges in both materials are conserved. So the number of charges that are added here, of electrons that are here, and the number of charges or the number of electrons that are left here. Do you understand? So the law of conservation of charges is obeyed. Right now, how do we charge by contact? Now, these are the two methods by which we charge conductors. Charging by contact and charging by induction. These are the ways by which we charge conductors. Now let me clean that part of the board so I will explain how charging is done. Now, how do we charge by contact? Now, if I wanted to charge a sphere, so the first thing I must do is that I must first place it on an insulator. If I place it on my hand, the sphere I want to charge, my hand is a conductor. Humans, okay, I didn't add that. Metals, graphite, and human body is what? They are, excuse me, they are all conductors. So if I place this sphere on my hand, it's going to be discharged. And what will happen is that the charge is going to be earthed because especially when I'm not wearing an insulated footwear, so if I'm not insulated in any way and I'm in direct contact with the ground, the charges from the sphere are going to be earthed. And I'm going to explain the concept of earthing in a jiffy, so just stick with me. So I want to charge this sphere. So if this sphere had no charges, or maybe it wasn't charged before, so as a conductor, it's going to have equal number of positive, negative, positive, negative, positive, negative, positive, negative charges, positive and negative charges, positive and negative charges, like this. Now, I now want to charge it. So I'm going to bring a piece of material that is already charged. So let's say I get a piece of material that has a negative charge. So what do? I bring it close to it. What happens is that these charges reorganizes the charges here. So what is going to happen at the end of the day is that this guy that has all negative charges, by the time it gets close to this sphere, notice because it is negative, we know that from the law of electrostatics that positive and negative charges attract each other. So the positive charges are going to come and aggregate here. So there's what? A reorganization of the charges. While the negative charges will move close to the extreme. This doesn't mean that this place will be free, but I'm just saying that, but there's going to be a sort of separation of charges such that the negative charges are going to move to one end and the positive charges are going to move to the other end. So the positive charges have now moved here. Why? Because this guy is negatively charged. So to charge by contact, bring a charged body close to an uncharged conductor. Notice this is what? A conductor. Call it a steel. So a steel sphere, any metal sphere. So the conductor. Now, I bring these negative charges here, then the charges separate out. So when they separate out, how do I now make this body to become one charge, to have only one charge? Now, while still keeping this charged body in position, I can touch this sphere because I am earthed. Now, first, the concept of earthing is that the earth is has a very large surface area and is composed of immeasurable amount of charges. Immeasurable amount of charges. So the earth cannot have a separate positive charge and a separate negative charge. Do you understand? So because of that, it absorbs all charges. What that means is that you cannot charge the earth the more. That, like, for example, now, if I cannot dump negative charges so much to the earth that all of a sudden the earth will just become negative charge. Negative charge. No. The earth has equal balance amount of them, very massive, in fact, almost actually unquantifiable amount of charges. So when I keep dumping negative charges, it has equal number of positive charges that balances it out. So by the time I touch it, the negative charges are going to pass through my body to the ground. And then, but remember, this conductor must still be kept in this charged body, must still be kept close to that sphere that I'm charging. Only that I'll just connect a wire or put my hand, and so this is the symbol for earthing here. So when I earth it, what will happen is that these negative charges are going to pass through this and get into the ground. Then while still keeping this guy in place, then this guy is going to remain with only positive charges. Now when it remains only positive charges, you can now remove the charger. Do we understand? So let's call it charger. So the positive charges will now be evenly spread across the conductor. So, and that is the concept of charging, and that is how an electroscope is charged. We're going to get into what that is in a jiffy. Let me clean this also. Let me pause the video. So how do we charge by induction? Now we said here, in charging by contact, it means the two components have to touch. Oh, I'm sorry. What we just did here is charging by induction. So that is how to charge by induction. That is how to charge by induction. Now, how do you now charge by contact? Contact means they must touch, right? So if they must touch, induction, so you notice they don't have to touch. It just has to come close. It just has to come close. But keep in mind that is how we charge conductors. So when it is charging by contact, I want to charge, so this guy is charged, see negative charge, and this sphere is uncharged. So what I do is I bring these charges, this charged body, to touch this body. Once it touches the body, then the negative charges, the electrons, basically flow to the uncharged body. And with this guy, so one difference between contact charging and inductive charging is that with contact charging, the body to be charged gets the same polarity as the charging body, the charger, right? While the induction charging, when you bring the charger close to the body to be charged, the body to be charged gets an opposite polarity to that of the charger. Does that make sense to you now? So I brought this negative charged body, negative charger, close to this, and this guy got what? A positive charge. But with contact charging, once they touch, the same charge gets to it. So that would say, we say the same polarity. Does that make sense? All right. So keep in mind that I said we are going to insulate this body before the process of charging. In fact, it's not. It's going to stay on an insulator, because if you place it on something that is another conductor, the charges can pass down. Do you understand? All right. So where is the dust? So that's charging. Now let's now talk about the gold leaf electroscope. The electroscope. First, the electroscope is a material. There are many more like devices. There are many devices that were developed in those days. So, for example, Benjamin Franklin was known for his kite, his famous kite experiment. So he used a kite, he project it very high. He's going to he tied a metal um, key to the base of that kite, and he's going to project it to a very high altitude. And at a point when electric charges, when thunder or lightning strikes, it's going to pass through the key down so there's a wire at the base of that key that connects to what is called a lightning jar. So a lightning jar was one of the devices that was also um, you know you know developed developed in those days. So and what the lightning jar was kind of a mini battery, but of course I have said it. The first battery was developed by Alessandro Volta, and we call that the power. But this one was such like a mini capacitor, the battery kind of, a capacitor stores charge, just like a lightning jar does. A lightning jar also stores charge briefly. But you see, I wanted to talk about what the electroscope is. Okay, so electroscope was one of the devices that were developed in those days, and it was a device that was used to detect the charge on other bodies. So if I wanted to discover the kind of charge that a body had, I would bring it to touch the electroscope, and the electroscope had the following components. Now there is a metal brass rod that goes into this place, and it has a gold leaf attached at the base here. These are gold leaves. So then there is an insulator here that separates this lead, this cover here. So there is a lead, the inside is lined with lead, you understand? Or any metal basically that is also a conductor, then it is connected to the earth. So it is earthed. So what happens is that if I want to discover the charge on this body, so once it is brought to touch this thing, if the charge on the electroscope is already known, okay, first, how do we charge the electroscope? We charge it by contact. It's easy to charge by contact. Just bring in this rod, this conductor that is already negatively charged, put it on it, and then this guy will, since it gets the same charge as that substance, with charging, the same polarity will be gotten, charging by contact. Once it gets the same, this thing will diverge. So the extent of its divergence is the amount of electricity that is the negative charges that is on it. Now, if you now bring a positive charge here, for example, a positively charged body, you want to know the kind of charge on it, you bring it close to that electroscope. Keep in mind that this is an electroscope. I call this brass rod, insulator, the gold leaf itself. There is a lead, this is earth. So you bring in a particular guy here, and it touches this guy. Once it touches it, since this charge is opposite to since we have charged this, remember we have charged this with negatively charged body by contact. This guy is now negatively charged. By the time you bring this body close to it, it's going to collapse this gold leaf. So this gold leaf will collapse, showing that the charge on this thing is opposite to the polarity of this thing. And we already know that this guy has been charged with a negatively charged body, so it's already negatively charged. So by that time, we can tell that this is the opposite polarity, which is positive charge. Does that make sense to you? Want to know the charge? So if it was a negative body, another negative body that was brought close to it now, and we have already charged this guy with negative charge by contact, negative charge by contact. We bring this guy close to it. By the time he touches it, it also diverges again to show further that this thing has the same polarity as it is. Remember, equal polarity, like charges, diverge, repel. So that is what is going to happen here. And that is it for electroscope. Now, another thing you should know is about lightning. Lightning. So we have, or at least you should have been taught that the thunder, the thunder is the sound you hear, and you know, and while the lightning is the flash that you see in the sky around rainy season. So when it just rained, so because it just finished raining, you are going to see so ions collide. I'm going to explain how it happens, but I just want you to know that thunder is the sound. You now notice that you would have seen the flash before the sound gets to your ear. Yeah, because we've said it before, light travels much more faster than the sound. Sound is 340 meters per second compared to the light, which is 300 million meters per second. Right? But the point is, now how does lightning form? Now lightning forms because clouds are made up of ions. There are many ions in the cloud. So if there is an ion buildup, so that in the cloud, ions might build up. Say for example, positive charges build up. Now when positive charges build up in the cloud, now that will be called the upward course or something. Well, you don't need to, know the, you need to know it, but for the context of Jamb, I don't think this is always asked. But just understand that positive charges build up in the atmosphere, and then because the ground is also, um, the ground it is also a house of charges. Think of it that way. So sometimes those charges can, go up, build up through high structures, So those charges could migrate up. So unfortunately, it could be negative charges that now migrate up. Now, when those negative charges migrate up, so what happens is that they, when they touch each other, it looks like there is a jumping of charges. So that jumping of charges is the spark that you see, that light that you see that we call lightning. So that is it, because the positive charges are built up and the negative charges are built up, that were building up in the clouds and the one that were building up from the ground, they met each other and then they resulted in lightning. Or sometimes it could just be positive charges from one cloud and negative charges in another cloud. So when those clouds come together, they meet each other, then you see what? Lightning also takes place. Those ones don't get to the ground. So the lightning that takes place that you see on top there, some of them don't get to the ground. The ones that get to the ground are caused by this one, where there's a building up of charge from the ground upwards, and then there's a building of charge from up the cloud downwards. So when those two causes meet each other, then they produce a spark. Now, the danger is that if it was on a structure, on a house that charge built up, and then, it's built up and built up itself. There's negative charges just kept building up, and it could reach up to that this thing, and that lightning happened. If that house does not have what is called a lightning conductor, a lightning conductor is basically a wire that can conduct electricity back to the earth. So it earths it back. So that when those charges build up from the ground at the top and they meet each other, in order to avoid shocking anybody that is maybe resting on the wall or touching a metal component in the house, in order to avoid that person from being electrocuted, what happens is that lightning conductor gets touched, the charges moves in the direction because it's a conductor. So the charges move in direction of that lightning conductor so that there is no build up, and then or the build-up is also is destroyed, and then the charges are conducted back to the earth. So that's the piece of wire, the long wire that you see from the top, somewhere at the top of the house, and then you see just beside somewhere in the wall is, buried in the ground. It's buried with metals into the deep part of the ground. All right, so that will be it for this video. In the next video, we're going to talking about static electricity. Here, we're going to start with formulas and calculations. So, but at least I hope you have understood the concept of electric charges. Do what to subscribe to the channel and click the bell notification so that you get notified whenever I drop all those videos. Thank you.